Hi, I'm Matt from Cleevely EV here in Cheltenham, and we're one of the first independents to concentrate on promoting and really working on EV. We started 3.5 years ago now, and we've seen some very interesting jobs for our workshop. I'm just going to run through a couple of those that we've seen in our workshops in the last few years, and mainly on Nissan Leaf. So Nissan Leaf, Renault Zoe were the two most popular EVs, are the first ones on the block that were fairly affordable and readily available. This vehicle's from 2017, but this generation, the shape of Nissan Leaf, are actually available and on the road since 2010. This is the Sunderland-built Nissan Leaf. So 2013 onwards, they were built in Sunderland, and the architecture internally, electronics, the way that it operates is very different from the Japanese cars that were imported from 2010 to 2013 that have an electric handbrake and a beige interior. That kind of denotes them, but the exterior, they are all very similar and all the same looking. You run an independent garage, you want to know, what are we seeing as an independent garage? What kind of things do we work on? So, aside of the servicing of these vehicles, and there isn't a huge amount to do, so I'm not going to run too much about that, but there is a few common faults now that we're starting to see on the Zoe with charging and with air conditioning and a few drivetrain issues, and with the Nissan Leaf, just going to run through three of the main ones that we've seen that give fairly dramatic symptoms and that may end up in your workshop. So with this vehicle, I'm assuming that to get any electric vehicle running, you put your foot on the brake, you push the start button, and it goes into a ready mode where it engages the contactors in the high voltage battery, and then you can move off safely. These vehicles, what we have seen on the Leaf for our first fault is that the car won't turn off. So it gets brought into our garage, so it's maybe successfully completed the journey, customer goes to get out, the car won't, it powers down, so it no longer remains a high voltage vehicle, but it won't go into a park. You have to make sure you apply the handbrake, which is more of a park brake rather than a handbrake as such. And you get lots of warning lights on the dash saying that the transmission isn't operative anymore, it won't go back into ready mode. You can essentially not turn the ignition off, and the car also won't lock, which can be quite cause the customer to be quite panic stricken. So after conversations with Hevra and working with them to do some circuit tests, obviously diagnostic testing to see what's communicating, what's not communicating, we found that it was a communication issue between on the CAN data network between the car and the body control module, and actually specifically main ignition relay circuit. So what we have here is this fuse box, which some of you may actually recognise if you work on Nissan generically, and probably most famously Nissan Qashqai wiper faults is what we've been changing this, but it seems like the Renault-Nissan group stuck with the same theory and ended up with the same problems across their range, where it purely is as simple as having an ignition relay fault, and on this unit we've ground away and we've put a standard 4-pin relay in the place of the faulty relay that occurs, which allows the vehicle to actually behave normally. Just disconnecting the 12 volt, you can make the car safer and able to work on. But what I wanted to point out with this one, although it seems very basic, is that the fundamentals of a lot of high voltage work, it all boils down to and can be affected by a simple 12 volt circuits that we all know and love and are very, very used to. So this is a case in point to help you guys out that not all faults with EV should be run away from. They may be just as simple as a 12 volt fault that you'll be very familiar with diagnosing or getting to the root cause of. But I will say that without the input of Hevra to help us get to this point, it wasn't something you come out and put your finger straight on. Another fault, and one that's quite scary that we've seen, is that electric vehicles, the brakes operate slightly differently. There's a lot of electronic control. Electric and hybrid vehicles use regeneration of part of their braking. So when you physically apply the foot pedal, depending on the amount of pressure and how quickly you press the pedal, some of that is actually automated by electronic brake booster, so that it allows the regenerative, the recovery of electricity from the motor back to the battery to happen without the physical brakes actually being touched. Scary on these Leafs, we've had 2 or 3 instances now where the brake pedal will actually go to the floor. You get warning lights as well, so traction, ABS. Essentially it's a communication fault on the brake electrical circuit, but in the case of one of the cars that we had, was actually a driving instructor car, the brake pedal would go to the floor, which is quite a scary experience for a learner driver especially. Again, with some wiring diagrams, piecing it together with fault codes you're going through, we've managed to trace this down to the brake booster. So the brake booster's at the back behind the master cylinder, so we've got that here, and it's ECU controlled, where the amount of pressure is monitored and also synthetically reproduced within the unit. So we're seeing these through the independent garage sector now because the independents are cheaper, but the main dealers eventually get to the diagnosis of the control unit and they have to put on new units. So you could be looking at a £3,500 bill to get to the bottom of this. So as I said, it's tucked down the back there, behind the master cylinder. Looks like a scary job, but it's actually not too bad to get at. A couple of hours work, and brilliantly, it's not actually a coded component. So we can just directly replacement from a breaker, get the customer back on the road, and ultimately, regardless of fuel train, that's what us independents are here to do. We are here to repair vehicles as economically and professionally as possible. This scary looking unit here is the PDM, or power delivery module. We've seen a few instances now where either the car, so what this is, it's sat on top of the motor stack, and it's the power delivery module, PDM. So fairly easy to access. You have to take the scuttle off if you're going to get to it, and obviously it's high voltage, so if you are going to start looking into this, then make sure that you are high voltage qualified and you are aware of the dangers involved. But once the car is isolated and once the high voltage is dealt with, the symptoms and the reasons we've got this one here is we've seen failures of non-charge, either on DC, which is the rapid charging functionality, where as you can see through this section here of the PDM, or through the AC, your standard 3-pin plug, or fast charging, which is controlled through these circuits on this side of the PDM. We've traced it down, which is what we do in events. We want to know what's going on, why is it faulty, that there's a short to ground in the lower half of this unit that actually damages 2 of the relays that monitor voltage through the circuit. So although there are fuses in here, and I wish it was as simple as just getting involved and replacing these, unfortunately it's not. It's a deeper problem, but we have found that, again, these aren't coded, and so that you can do direct component replacements and allow the car to get back on the road as economically as possible. But generally, EVs are fantastically reliable, and we are getting involved with some battery cell issues. On the very early Japanese Leaf that I mentioned earlier, we found that some of the cells are dying because they're 10 years old now. So we have a stock of cells here, drop the battery out, replace the cell, put the battery back in, off we go again. Which is a really nice in-depth job to do, and you get good satisfaction from the customer keeping their older EV on the road and it's not being wasted or binned. We also moving into battery upgrades, which is a really interesting topic, and one that you have to get over the CAN communication error, so it's not as straightforward as taking one battery out and swapping another one in. The way we teamed up with a Dutch partner who provide a CAN bridge, so they deal with the CAN communications. We install the bridge, then we can do the battery swap over and trick the car into thinking that the battery was always belonging to that car. So far from us as independents ever running short of work when the EV revolution comes along. It's just going to be a different type of work that we're going to have to get our head round. And certainly the looking after of the whole car with brakes, suspension, tyres, all that kind of stuff. There's still revenue to be made. It's just these kinds of areas now are something that you might want to start getting your head round. Get yourself qualified so at least you know some of the ins and outs of the way that the cars operate. And you'll be in a better position when you eventually start seeing them come through your workshop doors.
Hello and welcome. My name is Crook, and today I'm going to be talking about basic oscilloscope use. In front of me we've got a BMW X5 with an intermittent starting problem. We've checked it for codes, and the only code being flagged is an intermittent camshaft sensor fault. So today we're going to set up the oscilloscope to capture the camshaft sensor and look at some basic settings and compare the output from the oscilloscope with the output from a multimeter, so you can see the benefits of using an oscilloscope over a meter. So first of all, we're going to talk about the setup. The vehicle has got the camshaft sensor right at the front of the engine, which is really convenient for testing, and we have back probed the camshaft sensor, and we've got 3 connections, and we've got a ground, a live, and the signal. The channel 1 of the oscilloscope, which is the blue trace, is connected to the signal, which we have determined from a data source. Channel 2, which is the red trace, is connected to the supply, and the third pin on the sensor, which is the ground, we're using for the ground for the oscilloscope. Multimeters are also attached, and the multimeter is currently attached to the power supply, to the signal, and also to the ground. What we're going to do is we're just going to turn the key on and see what the multimeter gives and compare that to the oscilloscope. Before we look at those signals, what we need to do is look at how the oscilloscope is set up. So on channel A, which is the blue channel, as a starting point, we're using 20 volts with a time base of 200 milliseconds. On channel B, we're also using 20 volts, and we also, because the time base is common to all channels, we're also at 200 milliseconds. So let's talk about those two things just briefly for a second before we move on to seeing the results of the test. Channel A, which is the blue trace you can see on the screen, we've set at 20 volts. Why do we use 20 volts? Well, the vehicle obviously is fed with 12 volts from the battery, but when we start we expect that to go up to at least 14 volts. If there's a charging fault, that could go even higher, and we'd expect the car to get pretty grumpy above about 18 volts. So we can see that on the screen. However, if you have a look at the screen, the 0 point is in the middle of the screen. Now, when you're analysing signals using the oscilloscope, you want to try and get the image on as much of the screen as possible, which enables you to look at it in far more clarity. So one of the things you can do with the picoscope is you can change the scale. Simply select the channel, go to display, and if you change the scale on that channel to ×2, you've now only got 10 volts above and 10 volts below. But if we move the 0, just by grabbing the side down to there, we've now got 16 volts above and 4 volts below. And if we do the same on channel B, select channel B, go to display, change the scale to 2. Now, channel B is on the other side of the screen. Over here, and you need to move that side down. Simply click the box so the menu goes away. Once again, now you've got a nice full screen to analyse what you're doing, and we can see if we get a negative result or a positive result on the screen. But now we're using far more of the screen to look at the image. So what we're going to do is just going to turn the key on, and we're going to compare our meter with our oscilloscope. Okay, the meter's reading 12.1 volts, and the oscilloscope on channel A, which is the signal, and channel B, which is the supply, is reading. And if we want to know exactly what, we can just bring down the measurement, put that in the centre, 11.9, and then on channel B, put that in the centre, and that's reading 12.1. So at this point, there's very little difference between the meter and the scope. So if we move the meter onto the signal, the meter's now reading 11.8, and the oscilloscope is reading 11.9. What we're going to do now is we're going to start the vehicle and see what changes. We'll move the meter back to the supply. which is pin 1. I'm going to start the engine. Just move the measurement box out of the way of the images. The meter's now reading 13.8 on channel B, the supply, and if we put the measurement cursor in the center, the scope is reading 13.9. So very little difference on the supply. However, if we now move the meter to the signal, the meter's reading, it's very difficult to say, it's jumping around between 10.8 and 12.8 volts, but it's jumping around. However, the oscilloscope giving us an image whereby the voltage is at a level, it drops to 0, goes back up, is at 13 point something volts, drops to 0, goes back up, and the pattern repeats over and over. Let me turn the engine off and we can discuss what we've seen. So we switch the engine off so we can have a look at what's happening. Now what's interesting now is the oscilloscope has recorded what has been happening while I've walked back and forth to the vehicle, whereas the meter is now reading 0. So this is another advantage of the oscilloscope. If you're testing on your own, you can take the measurement and then analyse it afterwards, which is a very powerful feature for most technicians. So what we can see is, visually illustrated on the screen, is what the meter was trying to display. However, the meter only refreshes about every 4 times a second, so that's about every 250 milliseconds. However, when we look at what's happening on the screen, from there to there is only 200 milliseconds. So during that time, the meter has tried to capture the change in voltage, which is going from 13.6 to 0, back to 13.6, back to 0, back to 13.6, down to 0. And that's why it's displaying 10 volts, 11 volts, sometimes 12 volts, because it's maybe taking a reading and it averages out the reading over that period and then displays what it saw every quarter of a second. So it's maybe taking a reading and it's got that, maybe it's got that, maybe it's got that, maybe it's got that. So it doesn't actually refresh fast enough, because if those numbers were to change that fast on the screen, they wouldn't mean anything to us, we wouldn't be able to see them ourselves. So the meter gives us an average or root mean square reading of what happened to that voltage over that 250 milliseconds and displays it on the screen. Whereas the scope draws a picture of what happens, and the oscilloscope is able to do this millions of times a second to draw the image that we see on the screen. Where now we can see that we've got a nice, good ground signal from the sensor. We've got a good and constant supply voltage. All the little spikes that you see on the supply voltage are noise, electrical noise that the cables are picking up, despite the fact we've tried to isolate them away. There are fairly heavy current consumers and back EMF generators in the injectors nearby, and that is what you're seeing. This is interference or noise from the injectors mainly happening on the screen. So you can see a key difference between the oscilloscope and the meter is the ability to draw the pattern very accurately on the screen, as opposed to the average reading over the same period.